Hey physicists, today we want to talk about capacitance. So it's the beginning of how do we store electric energy, or how do we store electric charge is sort of the idea of where this is coming from. So when we talk about way back when Alessandro Volta, and then we're all studying this, they said, well, this is all well and good, but how can we use this? How can we make it more helpful? So the first capacitors, there were a bunch of them that all sort of happened around the same time frame. We have Ewald Georg von Kleist, who was German, 1745. Peter von Muschenbroek, he developed what is called a Leyden jar, or a Leyden jar, named after the city of Leiden. And that is this guy here that we'll talk about in just a couple of minutes. We have Benjamin Franklin. He was an American. He developed a Franklin square, and he literally took like a piece of metal and a piece of metal and held them apart, and those square shapes that they were, that's called the Franklin square. And then there was Michael Faraday, who was English, and what he wanted to do was he wanted to store these unused electrons for his experiments. Interestingly enough, his parents had a business that had a lot of oil drums, and so Michael Faraday was using the oil drums for his capacitor, and we now have named the unit of capacitance after Michael Faraday. So it's measured in farads is the unit for capacitance. So like I said, we would talk about the Leyden jar here in a second. So we have a Leyden jar here, and this is a newer form of this. So the original one would have been made of glass. There would be a piece of metal that's on the inside. So if I can pull this centerpiece out, which, my goodness, it's stuck so tight, vacuum sealed. So I have a piece of metal here. I just have a piece of plastic. You literally can do this at home. If you take a Tupperware bowl, a plastic bowl, wrap the inside with aluminum foil, and then wrap the outside with aluminum foil, then you have created your own Leyden jar or capacitor. So what that does is it allows you to charge one of the pieces of metal with one charge and the other piece of metal with the other, and the insulator keeps them from negating each other, or from distributing evenly and neutralizing each other. And so you end up with a charge on one. So maybe the outside of this is negative, the inside of this is positive, so that whenever you go to touch it, then you are either charging or discharging it, or if you go to touch both of them, you've created a loop that forms the circuit that allows those electrons to go. Otherwise, the electrons, that separation of charges, will remain there for a very, very, very long time, a very long time. It's one of the reasons why they tell you that if you go dumpster diving, if you're looking at old CRT TV, if you find something like that, or an old microwave, you should not open it up unless you know what to do and how to discharge the capacitor. And maybe we'll talk about that here more in a minute too. So the capacitor, it is a basic idea is that you have two charged conducting plates that are equal and oppositely separated by an insulator. So we have some kind of insulator that's in the middle here. What this does is the battery is going to take the electrons off of one of the plates and dump them onto the other plate. So the battery will charge the plates until the potential difference between them is equal to the voltage of the battery. So there are two things that can happen here. Either the battery is strong enough that it can take the negative charges. So originally this is negative, 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 negative. And then what happens is the battery pulls those negatives around and puts them over on this side. So now this plate is negative, this plate is positive. So if the capacitor is not as strong as the battery, then the battery will do this until the voltage is the same in the capacitor as in the battery. So if this is a 9-volt battery, then this would become 9 volts on my capacitor. Now, let's just say that the capacitor is not as strong as 9 volts, like it can't hold that much voltage. Well, what would happen is we would end up with so many electrons over here that they would start sparking over and discharging, and then the battery would flip them back again. You could kind of think of this as like the turn signal in your car. So the battery is pulling the electrons to one side, it sparks over, causes your light to blink on, then it recharges, the light is off, and then it sparks again, it causes it to blink on. Or you might think of these as like your Christmas tree lights, the ones that are blinking. Dinky, dinky, dinky. So that's what your capacitor is, the thing that allows them to blink like that. Now, like I said earlier, these will stay charged even long after the battery is disconnected. You have to be very, very careful with capacitors because they can kill you. Especially the really big ones that would be in TVs or microwaves. So the battery pulls the electrons from the positive plate, deposits them onto the negative plate, and then the insulator is what keeps them from jumping back over. So again, remember, it will do that until it reaches the voltage of the battery, or until it can't hold the charge anymore on one of the plates, and it will discharge over to the other plate. So if you picture here, I have a battery. And I have this electron that's coming out the negative side, going around, obviously not this slow. The electrons are going to travel at near the speed of light. So what we're going to happen is just a few questions here. Number one, what is flowing through the wire? Obviously, it's the electron that we talked about there. Number two, what function does the battery have? Remember that the battery is giving energy to the electron so the electron can travel around that circuit. And then number three, is this animation an accurate depiction of the behavior of the electrons in circuits? We said no, not really, because one, they travel at near the speed of light, and two, they're not necessarily going to travel in this straight line that just goes around. It's going to bounce all over the place in here, and it's going to bump into the next electron, which will bump into the next one, which will bump into the next one, and that bumping motion is constantly pushing the charge around the circuit, not as if it were going all the way around. But for the purposes of what we're talking about, we can just say for now that it goes around the circuit and it causes that flow of electricity or electrons. Now, let's throw a capacitor in here. We put two parallel plates in. What's going to happen is the battery is going to take those electrons and it's going to start pushing them from the one side of the plate to the other side of the plate. So notice how I end up with the plus plate on the left, the minus plate on the right, and as it keeps pulling those electrons around, I'm going to speed this up here a little bit. Notice how I'm going to get a stronger and stronger and stronger and stronger capacitor or capacitance there. So when will this stop doing that? Quick quiz from what we just talked about a minute ago. Remember, it will stop when one of two things happens. Either the capacitance will get to the voltage of the battery, or the capacitance isn't strong enough and it will discharge where the electrons will spark across the insulator or spark across the gap there. Okay, so it looks like I'm going to ask those questions that I just asked again. Will the charges build up on the plates forever? And the answer is no. It will build up until one of those two things happens. Number two, when will the charges stop flowing? We just talked about that too. And number three, why don't the charges jump from one plate to the other? And the reason for that is because there's an insulator in between and or the battery isn't strong enough to put that much charge onto one side. Okay, now, quick question. What I've done is I put a light bulb in here. When will the light bulb light up? And when we think about that, we have to think about when is the electricity flowing or when is the current flowing? It's flowing while the capacitor is being charged. So as the battery is pulling the electrons off of this left plate and dumping them on the right plate, the bulb is really bright, but then it's starting to lose the number of electrons that it can pull from that left plate. And so it's pulling less and less and less, and my light is getting dimmer and dimmer and dimmer until now it has stopped flowing because the capacitor has reached the voltage of the battery. And so there is no flow of electrons there, and so my light would be turned out. And again, that will be like our Christmas lights. As the capacitor is charging, the light is out. When the capacitor discharges, the light blinks. Or the same thing with your turn signals. Have you ever wondered as you're sitting at a stoplight, and you're watching the car in front of you's turn signal, and you're looking at your signal, and they're not lined up, and then they're lined up, and then they're lined up, and then they're not lined up again, where they're like blinking together or not? It's because they have different capacitors running the lights that are charging those. Okay, so a couple different examples of capacitors. This is what we might call, what I just affectionately call Swiss roll capacitor, where literally you take the two metal plates, you put an insulator between them, and then you roll them all up, and they look something like this. So where it's just it's a wrapped one, and it has the two prongs coming out the end there that you can see, and they come in all different sizes. So here was a smaller one. I have some really, really small ones too. There's another kind that's called an electrolytic capacitor. This is a ceramic capacitor, so basically you have your plates and then it's dipped into a ceramic that acts as the insulator. Again, that comes in all different sizes too. It would help if I don't put those right across my face, huh? Here's really even a really, really small one that you can see for that. And so what you end up with in this case is you have this one is the positive charge, the one is the negative charge, and they're connected to the different foils, to the two different foils, and that's what allows you to charge one plate up, uncharged the other plate for that. So how do we measure capacitors then? We're going to measure them by a value that is called capacitance. And it's the ratio of the stored charge to the electric potential difference. Now, remember earlier, what did we say is electric potential difference? Electric potential difference is another word for voltage, right? So if we're talking about a ratio, it's going to be a fraction. So I'm going to have a fraction of the stored charge to the voltage, and that's going to be my capacitance. Another way to think of it is, remember when we talk about relationships, we say, as the charge is increasing on this capacitor, then so is the voltage, or vice versa. As we're increasing the voltage on the capacitor, isn't the amount of charge that it can hold bigger? So I can take and say that that charge is proportional to the voltage. Now, when I want to change a relationship like that into an equality, what do we have to do? And we would have to add a constant, right? So I'm going to take and say that charge is equal to some constant times the voltage. And guess what that constant is? It's the capacitance. So the slope of that line tells me the capacitance that that has. There, I wrote over top of what I wanted to show you. So if I erase that. So we have the slope. What does that slope represent? It is going to represent whoa, skip way ahead. That slope is going to represent the capacitance that we talked about, that Q over V. Now, interestingly enough, remember how we talked the slope always means something, but so does the area under the curve always means something. And so when we take this, we can say the area is 1/2 the base times the height, half of the charge times the voltage. And guess what that is going to be? That is going to be the amount of energy. It's going to be the amount of energy that we are storing into the capacitor. Okay, so here we go. Q is proportional to V. That constant that we add is going to be the C. Now, the biggest confusion in this part of the chapter is don't confuse this C that's a variable with this C that is a unit. They're both two different things, okay? So we have the voltage, and we have the capacitance, and we have the charge. So remember, we measure charge in coulombs, which is this Q value, and we measure capacitance in what we would call as farads, and that is going to be measured in Fs. So in the equation, we have Q equals Vc, but then we would measure Q in coulombs, V in voltage, and capacitance in farads. So here is a quick cheat sheet that you might want to put in your notes somewhere or take a screenshot that tells you exactly what each of those variables are. This is the letter that you would see in an equation. This is the letter that you would see after the number, the unit that we measure those in. So as a sample problem then, we have a 1.1 microfarad capacitor that has an electric potential difference of 1.5 volts across it. So what is the charge on the capacitor? And then B, what is the electric potential energy that this capacitor will have? So if I take this, I can look at it and see that this is 1.1 microfarads. Remember that farads is a measure of capacitance, which in an equation is my C value. And then I would have an electric potential difference, which is going to be a voltage, which will be my V value. So if I'm looking to find the charge on the capacitor, then what relates those two givens is going to be that charge is equal to voltage times capacitance, or this is the home shopping network equation, QVC. Okay, so I want to find that Q value, so I'm going to plug in my voltage, 1.5. I'm going to plug in my capacitance, 1.1, and remember that micro is times 10 to the negative 6. It's the metric prefix, and that letter is the mu, the Greek lowercase mu letter, so 10 to the negative 6. And when we put that into our calculator, we end up with a value of 1.65 times 10 to the negative 6. And what do we measure charge in? We measure it in coulombs. So that's going to be our answer to part A. Now I'm going to switch colors here because that red is really hard to read. So the next thing, if we want to find electric potential energy that it has, then we're going to look at saying, well, hey, the energy is 1/2 the charge times the voltage. And do we know both of those variables? It looks like we do in this case. So we can say 1/2 of the charge, 1.65 times 10 to the negative 6, times the voltage, which was 1.5. And when you multiply those guys, you should end up with a value of 1.24 times 10 to the negative 6 joules. And so that's going to be how much energy is stored in that from that. Now, there are some ways to think through this. If you don't know both of these variables, we can take this equation, and this is sort of moving on from the sample problem. We can take that equation and say, hey, U is equal to 1/2 QV. Well, what if I don't know Q? Can't I substitute this VC in for that Q value? So this would be 1/2 of VC times V, 1/2 CV squared is another way to find the potential energy. Concurrently, we could also say, well, what if I don't know the voltage value? If I solve this for V, I can say V is Q divided by C. And then I could plug it into that and say 1/2 of Q times Q divided by C is going to be 1/2 over C times Q. So Q squared over 2C. So what we end up with is a set of equations that we can use that is going to be our electrical potential energy or capacitance energy that is either 1/2 QV if I don't know the, oops, I wrote a C there, if I don't know the voltage, or it could be 1/2 CV squared if I don't know the charge, or it could be, I totally said that wrong, 1/2 QV if we don't know the capacitance, the C value. And in this one, if we don't know the charge, the Q value. And then in this last one, the Q squared over 2C if we don't know the voltage value. So that gives you a way to think through each of those. So that's a sample problem. Now, moving on, okay. Capacitance also is determined by the construction of the capacitor. So remember, in physics, there are always two ways to find every variable. It is related to how big the plates are. So you can think that the bigger the plates are, the more charge it's going to hold, which will give me a greater capacitance. How far apart the plates are makes a difference because it's going to be harder for the charge to jump from the plates. And then also whatever insulator I put in the middle of that, that's also going to determine the capacitance. So this particularly, we're not going to go into the equation of this, although that's what it is. And then if we remember proportionality, if we want to make it a constant, want to make an equation, we would add a constant. We are not really going to do the math on that. So I just wanted to show you that to have you recognize the proportionalities and the equalities then. But you would potentially see this as a multiple choice question, which would be a great one, like which of the following is not used to determine the capacitance of a capacitor, right? Okay, some places that you might see this. So prevention and power loss. So the supplies the power while the battery charges. So for instance, if you are working in a hospital or you're on your computer at home and there's like a glitch in the power, then a capacitor will discharge just long enough to save your data and or get you going if there was a blip in it, that when the power is on, it redoes that. Car audio for amplifiers, this was an interesting one. So you picture those really, really low bass notes. They take a lot of energy. And so your car capacitor, the capacitor for your stereo on those bass notes, it will charge up when it's not playing the bass note. And then when it plays the bass note, it discharges the capacitor, giving the speaker the energy it needs to play. And then it recharges again while it's not hitting those bass notes. Pulse lasers, so high energy, short time lasers. Weapon detectors, I'm sorry, not detectors. Weapon detonators, so they would be particularly for nuclear reactions. So you would have the capacitor discharge, which would shoot the neutron into the uranium that's there. Flashes and cameras. So if you picture these kind of disposable cameras, have you ever, like when you push down the button, you hear the that is the capacitor charging up. It's a really high-pitched squeal that you'll hear most of the times from that. You can also, interesting and fun science thing to do, is to take these apart and make your own taser from them, because the capacitor is what you would use to make a taser. And then it also makes sense that that's a capacitor because as soon as you press the button, you discharge the capacitor, which causes the flashlight to, not flashlight, but the light to go off. Keyboards, so the distance between the plates here, you have one piece of metal up here, you have one piece of metal down here, and there's this insulator in between. And as you push down on this, these two get close enough together. Maybe if I use this in red down here and right here. As you push this, these get close enough together that it will spark between them. And if you were to pull your keyboard apart, you'll see that there's a whole metal circuit there so that whenever you look at, like, here's where my B button is, when that charge goes into the computer, your computer is defined to be like, well, that's going to be the B button. So a fun thing that you can do if you're early into programming is you can remap the keyboard so that when somebody comes and starts typing, then the B is really the M and the Q is really the S, and it really throws everything off and is a pain in the butt. So only do that to friends that you know you're okay with them hating you for the rest of your life. Fuel detection in airplanes. I was really surprised to find this out whenever I heard this, because I'm thinking like sparks and fuel, surely that can't go well together. But what ends up with this, and this is just sort of a really, really crude drawing. So here's my airplane and a wing, and the gas is down in here floating around, if my gas ever shows up there from me drawing it. So the gas actually acts as the insulator that's between the two. You have a metal here, and then that small, really, really small current or charge that flows through there, that as this gets lower, that dielectric, or that property, that insulator in the middle, it's changing. And so as that changes, they can tell how much fuel is left based on the change of that. Another one would be defibrillators. So you picture through, like, you're putting in the defibrillator, one on one side of your heart, one on the bottom side of your heart, and boom, it shoots that current through it. That's a capacitor that does that instant discharge into your heart. So major ideas when we're looking at capacitors, remember that it is the amount of charge per voltage that the capacitor can have. It's measured in capacitance, which is measured in farads, and it's a way to store electric charge, but it is very different than a battery. You would store it for items where you need just a really quick discharge of charge, as opposed to a battery where you would want a really long, slow flow of that energy. And that, in a nutshell, is the basics of capacitors.